for coming. And so I would like to tell you a story of coherent wandering in few-body land that we are trying to realize in ultra-cold atoms. So being the first experimentalists that are trying to come to tell you about ultra-cold atoms, I will tell a few words about what we have in the system, and then I will try to represent with the new developments that we have in our group. So what you see here is essentially this superposition state that we were able to create in the laboratory, and I will show you what is the consequence of that. Right, so I would like to also pay your attention to this afternoon talk of Reinhard Dörner to related ideas in different systems. So I'm going to talk about first some introduction of this experimental platform. I will tell you the traditional tools that were used before that. All these traditional tools are essentially incoherent spectroscopy. Then I will tell you about our wandering, which is coherent wandering, first in two-body land and then in three-body land. So ultra-cold atoms in experimental few-body physics research, right, is why it's so useful to use the ultra-cold atoms is, of course, in the property of these two-body collisions. So in two-body collisions, right, we have here, as usual, for very low energies, the wave function can be decomposed, right, into incident wave, and then the spherical wave that goes away, and we are getting the spectral, the scattering amplitude that is just depend on the scattering length, and this scattering length usually is of the order of the size of the potential. But of course, what we have in magic of ultra-cold atoms is the resonance scattering, and this resonance scattering is a Feshbach resonance. So we have atoms in the open collision, in the open channel, and then we have a closed channel that comes from different hyperfine states of atoms, and this closed channel can be tuned with the magnetic field with respect to the open channel, because they usually have some different magnetic moment. So by tuning the magnetic field, we can just bring one of the real bound state of the closed channel in resonance with the open channel free atoms, and this will cause the resonance scattering. So we have this nice tuning knob that allows us to change the scattering length, right, with this, which can be described with this very simple analytical formula. So the scattering length actually goes to infinity. It's positive on one side, and again comes from the other side with the negative side. So, and what is interesting is that, as usual, you have this essentially bound state for the positive scattering length side, and this bound state is the two-body bound state, which is universal and behaves as 1 over this the scattering length squared. Sorry. So, and this around this Feshbach resonance in two-body sector, we are having the Efimov scenario in three-body sector. So here, this is the position of the two-body scattering resonance, and this is the two-body dimer, right? So as we saw before, but in three-body sector, we have this infinite ladder of bound state in three-body sector, the Efimov scenario. Well, in our system of ultra-cold atoms, we have to add some boundaries where this scenario will make sense. So these boundaries are related to the finite range of interactions, right, from below. So something that is going to be the scattering length that is smaller than the R0, which is the van der Waals length, everything will be different and related to short-range physics. And if we are going to a very large scattering length, then we hit to a different limit, which is related to many-body physics, where the size of the scattering length becomes of the order of distance between the neighboring atoms. Okay, so now let me go to traditional experimental approaches, which are essentially the incoherent spectroscopy. So this, again, coming back to Efimov scenario. So we have 3 atoms essentially in our system. So these 3 atoms are sitting in the 3-body continuum. So now, having the 3 atoms, we can tune the knob, tune the magnetic field, and scan the magnetic field along this line. Right? Scanning this magnetic field along this line will allow us to be sensitive to the position of Efimov resonances, right? So the position here and here has enhancement of some kind of losses. So and this was the original method, experimental method, how to find Efimov resonances. This is related to 3-body inelastic collisions. So we have a finite depth trap, atoms collide within this, 3 atoms collide inside and form the dimer and a free atom, and the binding energy is released as a kinetic energy. Usually this kinetic energy is very large and atoms are lost from the trap. So this is the typical signal. So this typical signal is by chance from our system, of course, but this is something that we did many years ago, and it describes the maximum in a 3-body recombination from the negative scattering lengths and some other feature, the minimum for the positive scattering lengths, which is related to Efimov physics on a positive scattering lengths. So, but this is of course just a measurement of loss features, and these loss features are of course has nothing to do with the phase, whatsoever phase we have in the system. So this is the list of different flashback resonances in different homonuclear systems, and a nice summary of all this position of flashback resonances, Efimov resonances, which are related to the same experimental technique. Okay, now this is another experimental technique which is also based on incoherent spectroscopy. This technique is sensitive to positive scattering lengths. So where we have a dimer and a trimer. So this is, again, we start with 3 atoms, right? And then we apply a certain resonance modulation of the magnetic field. So if we hit the resonance here with dimers, then we see the signal of loss of atoms due to the enhanced formation of dimers. And if we hit the trimers, then we see the enhanced loss of trimers from the system. So we do that with a pulse, which is the modulation of the scattering amplitude, scattering lengths, sorry. And this is how a typical loss signal looks like. So this is, again, the number of atoms as a function of this time, the RF frequency. And this loss here has a typical 2 minima structure. So first one related to the dimers. So we hit here the resonance between the continuum state and the dimer state, and then we hit the second resonance between the dimers and trimers. And now we can scan, of course, the scattering lengths and see how the difference between these 2 minima changes, and we can plot the difference between the trimer and dimer state energy as a function of the dimer energy, and we can see how essentially the dimer and trimer energy levels come close to each other. So of course there's an inherent limit for this method, and this limit is related to the broad, the width of this resonance. So once the 2 energy levels comes closer than the widths, we lose the ability to distinguish between them. So again, the main conclusions from here is that all these previous experimental techniques are based on loss spectroscopy, and there are no coherent information So all information about the phase whatsoever is lost here. So let me introduce you to a different type of experimental exploring of this length. And let me start from the coherent wandering in two-body length. So in two-body sector, we have only one bound state, right? Essentially, not for real potential, but for our purposes, that's enough. And we are, again, modulating here the scattering lengths. And if this modulation comes in resonance between the continuum and the bound state, we can actually form dimers. So this is well known. But if we start to analyze the signal, so the question is how actually the molecular conversion efficiency depends on the length of this pulse. So this is what you usually expect to see if you couple the continuum with free atoms with the bound state that sits below the continuum. So this is a typical the molecular efficiency, the conversion efficiency as a function of the length of the pulse. So the longer pulse is, the more efficient the conversion, right, that you get here. So this is the number of molecules that you convert. And so these curves are just going to be, increasing without any special features. So it's a typical incoherent signal. But now the question is, what's going on if we are trying to actually increase the strength of the modulation? So if this modulation is, relatively weak in the amplitude, so let's try to increase the amplitude of this modulation and see what's going on in this case. So essentially, let's move to the rotating wave approximation. So this level will go into the continuum, but then we can actually realize that in case of a strong modulation amplitude, so this energy level will not stay the straight line. So if we are very weak, if you apply very weak modulation, then this energy level will be just a straight line. But then if we increase the strength, so we dress this level with the RF pulse strength, and then this dressing causes the shift of the energy level. So as far as this energy level stay in the continuum, there's nothing interesting happening. But if this energy level will be shifted below the continuum, right? So there is a gap that is opened between the dressed energy level and the continuum, and this gap will actually introduce some interesting features because of the interference that causes by two different paths that the system can go in this situation. So the first pass will be just to go in the continuum, right? But the second pass, the green one, this is the going into the continuum, but the second one is just to form the molecule and goes to this dress state. And there is a phase difference between these two different paths, and this phase difference can be recombined here on the second beam splitter, essentially, of the system. And we can expect to see some oscillations or coherence in this system. So this is the how the molecular conversion efficiency will look like as a function of the length of the pulse, right? And this molecular conversion efficiency should actually oscillate due to this interference effects. So this is the idea that was presented to us by our chairman of the session, by Chris. And we actually tried to realize this idea in the experiment. So let me show you first how to see that we indeed shift the energy level, right, when we enter into the laboratory. So this is essentially, again, the formation of the molecules. So we form the molecules as a function of the biased magnetic field. So we see the typical loss signal, and the minimum of the loss actually represents the position of the resonance. So now we can just see if we increase the strength of the modulation, we see that actually the position of this minimum shifts, right? So, and the shift of this position can be quantitatively measured and see if our first criterion could be satisfied here, if we can make a strong enough pulse in order to shift this energy level more than the temperature of the system. So, and this is actually the measurement of our system. And this measurement shows the shift, right, in the energy level shift as a function of the modulation amplitude. So essentially what we can say from this measurement is that the shift is much larger than the temperature of the system. So the first criterion to see this oscillation is satisfied. Let's go for the second criterion to be satisfied here. So this is essentially non-adiabatic effect. So we have to rise our energy level faster than thermal energy of the system. So this is how our pulse looks like in a laboratory. So this is the envelope of the pulse. So I don't show you the fast frequency of the modulation. This is just the envelope. So we have a typical on time and typical off time. And so this typical on and off time can be made short. So in our system, it's only of the order of, so it's only equal to 7 microseconds. And if we consider a temperature of atoms of about 1.5 microkelvin, it's related to 30 kilohertz. So if you compare these two rates, you understand that this ramping up and switching off, they are faster than the thermal energy. So non-adiabaticity criterion is satisfied as well. So now let's go to see how the signal looks like if we do our measurement here. So, you know, instead of decreasing or increasing the amplitude of the pulse, it's actually more correct to do in the experiment environment, actually to shift this strong pulse. So the amplitude of the pulse is not changes from one realization to other realization. But we actually shift our magnetic field where we start our experiment. So in this situation, for example, we just start very far away from the resonance, and then the amplitude, strong amplitude, shifts the resonance in resonance with continuum. So here we expect to see just non-adiabatic. Oh, sorry. Here we just see incoherent decay of number of atoms that we measure at the end of the sequence, saying that we actually form the molecules without any coherence, okay? So, and this is the theoretical calculation of what we should expect in the system, taking into account all the experimental parameters, as many experimental parameters as possible. Okay, so, and we see indeed that there is some monotonic decay here of this signal. But if we are going to now shift the initial position of the resonance, so we actually start to cross the continuum and enter into the gap. So we open the gap, and then opening this gap says that we are going to expect to see some modulation of the signal in the free atoms. So this means that we actually can distinguish, right? So we measure only free atoms. So anything that stays as a molecular is out of the resonance from our measurement system. So we are not sensitive to them. So and from here, you can see that, you know, our signal actually decays here. So we start to lose atoms, but then we actually regain them back. So they come back again here, and then they disappear again, then come back again, and then somehow it's decays out of the system. So here we have some oscillation frequency in the signal, and this oscillation frequency is relatively low. So we can increase this oscillation frequency if we move further away. So if we produce a larger gap, so producing a larger gap means that we should see faster oscillations in our system. And this is indeed what we see. We see again going down and then regain again, going down and regain again the signal. So we actually coherently form the molecules and then break them again into the continuum, but with the faster frequency here. So you can see that between the two minima here and between two minima here, a different time has passed. So it's just a demonstration that we can, form some coherence between the molecules and thermal atoms in case of strong modulation. And this a demonstration of, non-adiabatic effect in molecular conversion efficiency, which is related to the envelope of the pulse. Okay, so let me move forward to the coherent wandering in three-body length. So in three-body length, we are trying to create a coherence between the dimers and trimers. So we are going to explore the tail of this energy level, of the trimer energy level and the dimer energy level. So, and the idea is that we can form the superposition state between the dimer and free atom and the trimer by applying a short pulse. And this short pulse will be short enough in order to cover the distance between these two energy levels. And if we cover both energy levels, then we can create a superposition state. So it is allowed by some, energy separation in our system. So the thermal energy of atoms is about 20 to 30 kilohertz. So the depth of this bound state of the dimer is about 10 megahertz. And the distance between the two energy levels that we can explore is between this thermal energy and the widths of the pulse that we apply. So we create, once we apply the short pulse, we create this superposition state, right? And this superposition state can then be developed in time. So the time development will accumulate a different phase for this state and this state due to different energies. So this is dynamical phase that we accumulate during the evolution time, and we can measure this dynamical phase. Okay, so this is how it works in our experiment. So we apply the short pulse. So this is a strong and a short pulse. So I showed you before that we can make strong pulses. So now in this walk, we make this pulse very short, 10 microseconds. So to cover the distance between these two energy levels. And then we wait for some time and then apply the second pulse. It's a typical Ramsey interferometer sequence, though it's not a classical Ramsey interferometer. So here we have the free atoms. Then we create the first pulse, create the superposition state. Then the free evolution, we gain the phase difference between them. And the last pulse, project the system or try to project the system to free atoms. And then now this projection can be successful or unsuccessful with respect to the phase difference that is collected between this state and this state. And we are sensitive in our measurements to free atoms. So again, we measure only free atoms. We do not measure dimers or trimers. They're far away from the resonance, but they still stay in the system. So just I want to emphasize that again. There are no losses here, okay? So there are no losses. We don't measure losses. We measure the phase difference between these energy levels. Okay, so this is how the signal looks like for three different magnetic field or scattering lengths. Three different scattering lengths, so we can identify here the clear oscillations between, these oscillations in the number of atoms as a function of time. So the time here goes up to 150 microseconds, and we continue to see quite clear oscillations that are scattering lengths dependent. So we can do so. It's a bit difficult and small signal to noise ratio, and we have to extract from here the position of this resonance. So in this position of this resonance, to extract it, we use some technique which is closely related to some sort of Fourier transform. But then we collect all our measurements together. So you can see here the peak that is a bit above 100 kilohertz, and then we go closer and closer to the merging point between these two energy levels. So it goes to here, and then it's actually the signal disappears due to the finite resolution of our system, which is related to the temperature, finite temperature of atoms. So we said, okay, somewhere here should be the merging point, but then we said, okay, let's check that this merging point survives our next step, and then we saw that actually it does not survive, so we regain back the signal, and then, you know, wondering about what's going on here, we measured again and measured again, and we saw that the signal actually goes away again, as if the trimer survives the merging point. Well, so just to collect all our measurements, these are our old measurements from incoherent spectroscopy. Now, if we add our new measurements from this coherent spectroscopy, so the points are very large, but the error bars are very small. So the error bars are smaller than the size of the point. So this is what you gain when you measure frequencies. So it's a very precise measurement. So, and then here we get close to the merging point. Essentially, here we thought that the merging occurs, but essentially it didn't. And what we know and what we understand right now is that actually the trimer goes inside the atom-dimer continuum, and this it survives instead of just dissociate into atom-dimer continuum. It actually survives into this atom-dimer continuum, and we are still working on complete understanding of this effect. So let me conclude here that you know, this new tool for few body physics research is a coherent spectroscopy, and having this new tool, you can really measure some additional information on the system. For example, measure the decay mechanism, right? So, and the results that we've got from this distance interferometer are different from what we actually expected or anticipated in several facets. So first is that actually, you know, this was strange behavior toward the merging, and there is no merging. It's actually crosses into atom-dimer continuum instead of merging with it. So, and the lifetime of the Efimov trimer seems to be too long. So, since so this last months we actually work on this question of lifetime of trimers. So, in order to measure the lifetime, we have to actually change our strategy, how to measure the atoms. So instead of measuring the remaining atoms, we actually start to measure atoms that participate in this coherent spectroscopy. So this is, you know, just an image from our recent work where we measure a few tens of atoms up to a few hundreds of atoms. So this is a different type of measurement in order to measure the atoms that participate in the coherent spectroscopy. So this is the most important slide. These are people who are involved in this work. So I have a very so this Yakov is the main driving force in all this experimental effort and theoretical understandings around what's going on in this coherent spectroscopy. And Rui was the main driving force to work on Stuckelberg oscillations in two-body sector. So, and we have two more students that are working on a bit different projects, and these are our collaborators. So if you have questions regarding the understanding of what's going on, so address them. Jose should be responsible to answer the questions for three-body sector. Paul should be responsible to answer for the two-body sector. So if you want to understand a bit more about Stuckelberg oscillations, Chris should be able to answer you. And if you have any other questions for me, I would be glad to answer.
Lev, there was a plot I didn't understand. If you could go back a few slides, it shows a series of, it shows the peak and how the peak changes. Keep going back. There, exactly. So I see omega, I see, you're plotting capital A, but should that be little a or something like that? Is that really the amplitude of the drive in that direction? I see the y-axis, I mean, seems to be capital A.
Right. So this is, this is the, if you just have a look here, so this is the capital A. I mean, the number of atoms oscillate with some sinusoidal.
So why does the strength of, that's the,
I mean, this is a sort of Fourier transform, right, that you're seeing here.
Okay, so maybe I understand. So there's really two different y-axes. One is the y-axis of the individual little plots, and the other is presumably
right. I mean, okay, so
that's little a, maybe.
So they are shifted.
Yes,
just artificially shifted. Right?
Yes,
with the offset.
What do the different colors represent?
Well, just to say that, you know, to understand, to have any understanding of this picture, right?
Yeah.
We just color it with different colors, just to say that this is.
I'm just asking, are those the different traces taken at different magnetic fields?
Different magnetic field.
Okay.
Absolutely.
Sorry, thank you.
It's an artificial shift. I'm sorry for.
No, I understand. I just
forgetting to say that.
I got it.
What's the role of the direction of the magnetic field?
Yeah, okay. So the magnetic field that we apply here, this is the, so it's coincide with the direction of the bias field that define the scattering lengths in the first place. So we essentially really modulate the amplitude of the magnetic field. So we consider it as just a simple modulation of the scattering amplitude, scattering lengths. So the value of the scattering length is modulated, and the frequency of the modulation should be at the resonance between the continuum and the bound state. And there is no spin flip here, so there is no, it's not perpendicular to the biased magnetic field. It's really parallel to the biased magnetic field. And we consider it really as just the modulation of the scattering length value.
Maybe an add-on question, very, very trivial one. Does the scattering length depend on the direction of the two particles with respect to the defining magnetic field? It must, right? There are two axes. There is a magnetic field, and there is the connecting axis between the two particles for which you want to talk about the scattering length.
Right. No, as far as I understand that, the magnetic field is not, the direction of the magnetic field does not define the scattering length. So the scattering length is defined only by the amplitude of the magnetic field. So it's, in a sense, there's no spin that is involved in the story yet at this level. The scattering length is just defined by the value or the amplitude of the magnetic field, right? So the Paul probably can tell me. Well, yeah, so the S, right, so this is the, right. So Eric said the answer. So
yeah, as Eric
the answer
said,
is that the S-wave
S-wave
scattering is just the, the symmetric scattering. So, and you don't have any particular direction in the space that would be responsible for, different value.
Might have to push a button.
There, okay. Yeah, I have two questions. One is, maybe I just missed it, but when you apply this pulse sequence, what scattering length do you start at, or how does it work?
So what do you refer to?
Oh, I mean, you're varying basically the scattering length. So A initial is, it's just the point where you're hovering over in the energy diagrams.
Right. So for example, here, right?
Oh, okay.
So the scattering length, so is defined by the magnetic field, right? That we are setting here. So we are setting in the beginning, we set a certain magnetic field to define a certain scattering length. That's the bias magnetic field. So this bias magnetic field is quite large. It's about 900 Gauss. This is where the Feshbach resonance is, right, for our system. So the modulation of all these pulses are about the modulation of few Gauss, 1 Gauss, 1.5 Gauss, around this bias point.
Yeah, and then I have another question, which is, so when you see sort of this trimer pass into the atom dimer continuum, I mean, in these sort of little toy superpositions you've written there, is there time enough to see something like a decay of the oscillations or a damping of the oscillations? Do these things have a width, or is it just, does it change when they become a continuum?
So that was, of course, the first, you know, our first thinking about that was, let's try to see the decay of these oscillations, because that would be the essential information out of the story. We are still thinking of that. This is correct, but it's turned out to be very difficult to extract from the experiment. So it's much easier to extract the frequency. So that's, you know, even if the signal to noise is very small. So in here, we have about 20,000 atoms at this stage of the experiment. But the number of atoms that participate in this formation of dimers and trimers, so superposition state, the number of atoms is only a few hundreds. Okay, so the signal to noise ratio is really small. So we, in order to get this nice signal, you had to spend a couple of weeks in the lab to get this one run, and if everything works correctly. So there is something like about 2,000 of measurements here that are collected together to get quite a nice statistics. And then you start to realize that there is a problem, right? If you try to measure something that decays, if you start from the signal, which is about a few percent, something like 2 to 3%, and if you try to see decays, you can see decays, but you cannot decide what is the time scale. That's exactly the reason why we actually changed the strategy. So we don't want to, so we have to increase our signal to noise ratio from 3% to 100%. Then we will be able to tell everything about the decay mechanisms. And there are many different questions which are related to the decay mechanism. There are different decay mechanisms that we expect to see in the system. So first can be related to the lifetime of the trimers, which are already longer than we would be expecting. Than what we expected in the beginning. So they sort of live for much longer than you could imagine. There are many mechanisms that should be responsible for not surviving so long time. So it's another puzzle here. And in order to attack this puzzle from the experimental point of view, we really changed the strategy. So we want to measure now the atoms that participate in this switching between the, so that stay in the bound state, instead of measuring the free atoms. So we want to remove this background completely and measure only the atoms that participate in this story. So it's a change in the strategy. It took us some time to do that, and also a broken laser in the middle. I mean, it's, yeah, just, you know, life of the experimentalist.
Lev, could you show your, I think your last transparency when you see the trimer passing the atom dimer threshold? Yes, yes. Could this be related? I mean, this part below the threshold that the atom dimer threshold, to the virtual state of the trimer?
Yeah, well, this guy sits just there. I can probably answer. Well, we are sort of the last year we are fighting together to understand what is it, and it goes like a Foucault pendulum, you know, between the interpretations. What we are sure in that this is the case, not the one. So I mean, probably I forgot to mention that, but in our experimental measurement, we cannot distinguish between the two possibilities. So the one possibility is that this should be, it can be rebound back, okay? So now that was our initial interpretation. When we saw that in the experiment, we say there is no way the trimer can survive in the atom dimer continuum. That was the immediate reaction on what you see, right? So, and then we said, okay, if this is the case, then it should rebound and go back again. That was the initial interpretation, and that was actually, you know, you can find it in this archive. This is what we wrote that time. But then we realized that this is wrong. So based on many different, approaches to the system and calculations that Jose did in a recent year. And we just realized that this is not what is happening. What is happening is this guy, right? So the direction that, the direction that is in this direction. So we know, now we absolutely sure that this is what is happening. So now what we do not know yet is why this is happening. So it can be virtual state. It can be a long-range physics, it can be short-range physics, it can be whatever it is. So partial answer will be probably answered tomorrow, because, you know, this is a running up walk. So I don't know what I will know tomorrow, because Jose is not always telling me what is going on. So you would probably see some answers tomorrow when he is presenting his talk.
I don't think it's on. I'm not going to be talking about. It's not on. It's not on.
Okay. I'm not going to be really talking about this tomorrow, so it's better I say something now. The numerical calculations, they do show this trimer being above the atom dimer threshold, right? Now, I'm not entirely sure what you mean by virtual state, right? But in these calculations, there is a barrier, right, in which that state lives below that barrier. That barrier, it so allows the trimer to be above the threshold.
So it's a shape resonance.
It's a shape resonance. I mean, in our language, we call shape resonance.
But does not depend on the trap.
Does not depend. I have no trap in my calculations.
When you're looking at the atom, the atom dimer coherence, and you cross where it becomes unbound, does it go through the continuum, or does it stop, or can you ask the same question for the two-body problem? This is for the three-body problem.
You mean at the position of the Feshbach resonance?
Yes. Mm-hmm.
So if you go really here, right? So you are relating to this point.
Yes, right.
So in two-body sector.
Mm-hmm. What was that?
I would say, you know, this is what I would like to say immediately, but I think that, you know, probably this is a question also for, you know, if you go to a narrow resonance, it's probably possible to do such an interesting, you know, addressing to address your question. It's a different type of question, but it's actually, you know, Paul can say you that not always dimer disappears. This is what I learned working with Paul and Jose. They not always disappear, so it can survive, but it will survive if you have a narrow resonance, so narrow Feshbach resonance. And we do have narrow Feshbach resonances here in this story. So we can probably do this and probably measure something similar in the case of a two-body physics. It would be probably less difficult to answer the question why it is survived, because this is two-body problem. So it's only Paul. Paul makes calculation fast and can predict us what will happen. But yeah, I think it's possible problem. Yeah.
Thank you. Yes, there's we have some pictures in the old 2010 Feshbach resonance paper, review of Feshbachs that shows very narrow and very broader resonances. Some narrow resonances, if the pole strength that we measure dimensionlessly call the S resonance parameter, that's much less than 1. The resonance survives above threshold as a distinguishable quasi-bound state with a well-defined complex energy, with a real part that ramps more or less linearly with magnetic field, and an imaginary part that's small compared to the real part. But so the two resonances in the lithium channel you're working with, one is narrow like that and one is broader, and the one you're working with here is the one that's broader. So it probably doesn't have a distinguishable two-body state above threshold. But the other one, which is below 800 Gauss, will. But that one hadn't been studied experimentally yet. So,
Did you have something short, Eric? We're about ready to wrap up.
I guess if Jose is not talking about this tomorrow, then I want to ask him now, do you have any further insights for Lev and for the rest of us about really long, the seemingly very long life of these states?
Well, I will talk about lithium-7, but not specifically the dimer crossing. But my calculations, the lifetime, it is short, right? The lifetimes of the trimer that comes out of the calculations are tens of microseconds at most.
That's one of the reasons we are still, don't tell anybody anything about that.
Yeah.
Okay, let's thank Lev again, and Jose.